Good morning. So today I'm going to talk about movement patterns. So movement patterns was especially developed in the beginning of the field. So when the field started up, there were a lot of papers on movement patterns. And I think lately it's been going down a little bit, and I think maybe there's a reason for that. But I'll try to discuss that in this lecture today. So, as I said, much of the early work focused on finding movement patterns, and there are a lot of examples. Like there are lots of papers on flocks, so more or less similar to moving clusters. There are swarms, convoys, where they try to say something like they follow each other. Leadership, single file, popular places, and many more movement patterns. And the idea originally was that you wanted to find definitions of movement patterns that are useful from an application point of view, and still computable, right? Or maybe even the other way, the patterns that are computable but still useful, right? And this is actually a tricky trade-off when you talk to experts in other fields, to try to get a handle of what they find useful and still define it in such a way that you can compute it in reasonable time. Okay. So this morning I'm going to give a few examples, and then I'm going to go into details for one of them, or maybe even two of them. So I will say that the number of entities, so the number of trajectories is n, and the length, the maximum complexity of the trajectories is tau. Okay. So in most cases, of course, there's a big variation between the size of trajectories, but I'm just going to assume that the maximum complexity is tau. So let's start with the groups. So, and as I said before, there's just lots and lots of papers on movement patterns for groups. Probably the earliest ones in early 2000s, and then it's been going on for the last 10 years. And in general, what they've been doing is saying things like, what we want to find is a group of animals or a group of entities, and we say they form some kind of group or a flock if at each time step they are close together, right? So most of this early work, they assumed that all the timestamps are synchronous, right? So we get the coordinates of each entity at the same time, right? So this is a problem, because this is usually not the case. So how do you handle this? So now they're saying more or less, okay, that we're following one trajectory, and we get time t1, time t2, time t3, and so on. And then we follow some other trajectory, the time t1, time t2, time t3, and time t4, and so on. So this is hardly ever the case, right? When you get your GPS readings, for example, there's usually some delay, and if you get the data from animals, they just measured arbitrarily times. So how do you handle this? So a lot of algorithms, especially the early work, assume that all the data was synchronous. So what can you do about this? Well, of course, you could just say, right, say instead if it's not synchronous, I have t prime 1, t prime 2, t prime 3, t prime 4, and I can just increase the complexity of my other trajectory, right? So I could say something like, well, I introduce a vertex here, which is at t prime 1, I introduce a vertex here at t prime 2, t prime 3, and t prime 4 maybe. And then I would do the same thing at the other. Okay, so t prime So we would have T1, T2, no, yes, T2, and T4. But of course then the complexity blows up, right? So if you have n trajectories and you would do this for every trajectory, you could get quadratic size. Right? The other problem with this is, so you would like to avoid it, right? Which is more or less impossible. The other problem with this is that one of the most common techniques we use is to simplify the data. And if you have a model where you assume that the data is synchronous, then again you cannot simplify the data, right? So I think there are a lot of algorithms using this model, but I think you have to be a bit careful with this model. Preferably you would like to do it for asynchronous data. Anyway, that's just a warning for the data model. But let's look at this group algorithms anyway. So we have a set of 4 trajectories, and we track the entities along those trajectories. And say that we want to look for a group size or flock size of size 3. Well, here they're quite close to each other. So if it's within some threshold, then you mark them as a flock or a group. And then we just track to see how long they stay together as a group. So you see this is a fairly easy approach. And then when they spread out, well, then the group is finished. Okay, so here you would have some kind of flock structure or group structure. Okay, and there are a lot of different versions. So, for example, you can have a fixed subset, so the entities within the group cannot change. Or you can have a variable subset, so an animal can come into the group, and then maybe it will leave the group, and it will still be called a group or a flock. Variants of this is also, for example, meet. Right? So you want to decide, are there M entities that meet in some area? So there you want them to be close to each other at the same point in time. And there's another variant which is maybe less natural, but you want to see if there are M entities inside or in an area at any point in time. But it might be different entities. Okay. And there are lots of variants here, so I'm not going to give you a running time for this, because you have to look into the specific setup that you're looking at. Okay. Another one is convoys, which is just slightly different. So here they define, so let's say we have X is a set of entities, and again we have the M is the group size, in this case the convoy size, and we have a distance threshold epsilon. And then they say that 2 entities are directly connected if the epsilon disks intersect. Okay? So if these intersect, then they're epsilon connected. And then, are directly connected. And then you can say that 2 entities, xi and x5, for example, they are connected if there exists a sequence x2, x3, and x4 of entities such that for every pair, there's a pair that are directly connected. Right? So it's just saying that the epsilon disks form a connected component. And then they are connected. So using this model, there were quite a few papers in the data mining community. And it's a natural model, I think. So it definitely captures things like a convoy. However, it also, of course, any kind of group will also be captured, right? And a lot of these papers are in the data mining community. So there are a lot of experimental results, usually for a specific data set, but there are no worst case running times for this. So that could be an interesting thing to do, to actually look into what are the running times, the worst case running times for these algorithms. Okay. Okay, leadership and followers. So this is slightly different, so that's why I'm talking about it. Again, I'm not sure about the usefulness, but let's look at it anyway. So you say that you define a front for an entity, and that's some kind of area like this. So it has its apex at the entity, and then it looks forward in some sense with some angle. Okay, and so what do we mean with a leader? Well, I guess preferably it should not follow anyone else. So it shouldn't have anyone in front of it that it's kind of follows. And it should be followed by at least, say, m other entities. So that means, say, this guy might be a leader if he's not following anyone else, and all the other guys are following him. So that means that he's in the front of the others. Okay. And this should hold, of course, during some minimum duration of time. Okay. So here you would define the leader and the followers in the same way. The problem, so this looks okay, but I think when you try to apply it to some real data, the data is usually so noisy, or it contains so many terms, that it's very hard to define something like this. But again, I haven't really seen any experimental results on it, so it could be that there are some data sets where this would work for. Right. Okay, so again, there are a lot of different settings, and in general, the running time is roughly n squared tau log tau n. Okay, popular places. So here you want to, in the simplest version, you're given a square, and you want to detect if this is a popular place or not. So are there a lot of entities that visit this place? Right. So let's say we have, how many do we have? 1, 2, 3, 4, 5, 6. So let's say we want to decide if there are 5 entities that visit this place. Okay, we get 1, 2, 3, 4. I have no clue what happened. Anyway. Okay. So here I think about 5 of them visited. So it's a popular place for 5 if you set m equal to 5. Or less, of course. Okay. And this, in a continuous model, you can do this in roughly tau squared n squared time. And it was also shown that you cannot actually do any better than this. And for the discrete model, where you only look at the vertices, then you can do it in tau n log tau n time, and you cannot do it any better again. Okay. So let's look in a little bit more detail for one example. So this is for the single file. So do you know what a single file is? So it's like if you go off behind each other for a long time. Right? So it's one of these things that are, when you see it, it's very easy to say, well, this is a single file, but how would you actually define something like this formally? Right? So just look at some examples, and maybe we can discuss it a bit. So this guy is walking, and the other guy is following him behind him. So here it seems fairly natural to say, well, these two they form a single file, right? At least, I mean, again, maybe we should look at it as again. And, oops. No, this seems fairly natural. I think, this seems to be this guy, the second guy, is following the first guy. That seems to be a reasonable assumption. Okay, but what about if we change it a little bit? Like this? Is this following? I don't know. What about this? Well, if we look at single file, this should not really be a single file because single file should have a linear order. Right? It's like ducks walking behind each other. Right? But how do you detect something like this? Well, this seems to indicate that you should have some kind of pairwise order. So I guess what we can all agree upon is this is a single file. They all walk in a nice straight path, or there's a nice linear order. So let's see if we can try to define something like this more formally. The thing I want to define is when one is following the other in the single file. So let's skip the order for now. Just say I want to decide if this one follows this one. Okay, so right, so the user will have to specify the delay, or at least the accepted delay. So, for example, say that one of my entities are here at time t1. So say that this is a t1, and we have x1, and we have x2. And say that your x1 is your leader. Well, at some point in time, you would like x2 to be close to where x1 was. Right? That would be the definition of a single file. So you would like this guy to be somewhere close to where x1 was before. But you want this to be at some time delay, within some time. So if x1 was there at time t1, well, then you would like t2, x2, to be there at time t2, which might be something like the time t1, plus some minimum value tau min, to t1 plus some maximum value. So you want the guy that is following to be close to where the other guy was before, but within some kind of time interval. Okay, so let's see, can we define this more formally? Okay, so following behind. So here they are moving, the two of them. And these are their original positions. So you want the second guy to be within distance epsilon at some later point in time. And this later point in time should be fairly restricted. Okay, so you want this later point in time to be within some time interval. Oops. So this should be an AND. So, okay, so this looks a bit tricky, but it's actually quite easy. So let x1 be an entity with the parameterized trajectory f1, and that's in the time interval s1 to t1. And let x2 be an entity with parameterized trajectory f2 over the time interval s2 to t2. Okay, so S2 should be within. So this just says that S2 starts later on. Right, that's all it says, and it has to end later, right? Because it's following, right? So it has to start later and end later. And so we say that entity x2 is falling behind x1 in the time interval s1 to t1. If there exists a continuous one-to-one correspondence sigma between the first time interval, that is for the first entity, to the second time interval, that is for the second entity. And the restriction we want on this one-to-one correspondence is that the start time, the parameterized start time for S1 is equal to S2. Right? And then we want for all the points, all the timestamps in the first time interval, we want it to be mapped within tau max and tau min to the time. Right? So this is just the time mapping, and the restriction is that it has to be close. The spatial distance has to be close. Okay. So it just says that if you look at the time interval, say S1 to T1, and now I look at the time interval S2 to T2, then every point here in S1, T1 has to be mapped to some point, sorry, this will be T, so these should be roughly T, oh no, I did it the other way around. Let's see, how do I do it? So T1 should be mapped. Yes. So it should just be mapped to a point in the interval T minus tau min to T minus, T max and T minus T min. So it should just be mapped to one point in here.
Don't you want to add something like S2 minus S1 or something?
Yes, I need to do that, doesn't one? I guess this one has to be this, right? Something like this?
Yeah, well, yeah. So S2 minus S1 plus what is about there? So you shift by S2 minus S1 and then you add.
Yes. And this is S2 minus S1 plus T. Okay, so it wants to find, so for every point in T in this interval, you just want to find one point, say T prime. And for these two time points, you know that the position of the entities at those two time points should be within epsilon. Right? So let's look at it. So we have the two trajectories, and maybe this is their movements. And now what you do is more or less reparameterize S1, right? You reparameterize it such that these two constraints are fulfilled. So you slow down F1 so that they more or less move together, and at every point in time they are within epsilon from each other. So for this we use the Fauché distance. So I'm sure you by now remember what it is. So just remember that we walk from the bottom left to the top right in the white space, then the Fauché distance is at most r. However, this constraint is just saying that we need to look at a diagonal. So we constrain the movement of one of the entities to be delayed in time. Right? So they have to be close to each other, but with a delay. And that's the same as saying that I only need to look at this diagonal. Right? And so the definition of the free space diagram in this case is just so the white space is all pair of points, ST, such that the distance between the position of entity 1 at time S and the position of entity 2 at time t is at most epsilon. And the difference in between t and S is not too big in time. Okay. Good. So the running time for this is tau plus k. So tau to just go through the input. But then, because we look at, usually this will take quadratic time. Right? It will take tau squared because we have a complexity of the vertical axis of tau and the horizontal axis is tau. However, when we restrict ourselves to a thin diagonal like this, a thin slab, then the complexities of this is usually linear. Right? If these two are very big, then of course it could cover the whole free space diagram. But for most cases, this will be a fairly narrow slab with linear complexity. So then the running time will be roughly linear. So if we can say that who follows whom, so we can say that one entity follows the other, then one can determine in tau k squared time during which intervals one trajectory is following the other. Right? So it can change, so we can just do between every pair and every directed pair, ordered pair. So we can compute all the time intervals where one is following the other. And the other way around, we can do it between x1 and x2, but we can also do it between x2 and x1. So if the order is specified, then we can compute a free space diagram between every pair of consecutive entities and then compute all the time intervals in n tau k squared time. Okay, so if no order, then we have to compute all the following behaviors for every pair of entities. Right? So we could get something like this, for example, that x4 follows x3 in the time interval between 3 and 8 and 14 to 21. And then for a specific time, we can just see if there is a linear order where each consecutive pair follows the one in front of it. And that this will take n squared times tau times k squared. Okay. Good. So any questions on this? So I think the nice thing with this paper is, again, it uses the free space diagram, I think, in a kind of a novel way. So I remember in the paper they do some experiments just with the authors wearing GPSs when biking. And you can see that there is some kind of following behavior. But I think that's a very structured example. So it might be interesting to see if one can use this for some other data sets. Okay. So the last topic of today is how we define and compute the structure of groups, moving entities. Okay, so this is a paper by Bochen, Van Krevel, Speckman, and Stahls, and it's just recent. It was just published last year. So the thing is, we want to see what we want to do is so we can compute these groups, but we want to see how they evolve during time. Right? They could be groups that merge with other groups. It could be merged that split. And we would like to see how this structure changes during time. So let's look at two groups here. They meet and they split. Right? So in this case, we probably would not like to consider them as one group at any point in time. Right? I mean, they just more or less happen to meet each other, right? But it's not really forming any kind of group. So, but here, on the other hand, now we have two groups. They go together for a little bit, and then they split. Okay, so we have a merge of two groups, and then we follow by a split of the single group into two. And it might not even be the same entities in the two groups. So you might not even have the same two groups that you started with that ends, right? Okay, so we're going to use the same definition as we used for convoys. So this epsilon definition. So 2 points, x and y, or two entities are directly connected if the epsilon disks x and y are intersect. And we say that they are epsilon connected if there exists a sequence such that they are directly epsilon connected, and this forms a connected component. Good. So I mean, it's easy to see that a set of entities it's epsilon connected if all the entities in this set are pairwise epsilon connected. Right? It's just a connected component. Okay. So let's say that at time t, we have the set of connected components. So denote that by C of t. So in this case, we'll have 1, 2, 3, 4, 5 connected components. So that will be our 5 groups. Okay. So what is a group? Well, we will have 3 criteria. So it should be big enough. There should be enough entities participating in the group. So let's say in this case we have 4. And they should be close enough. Right? So they should form a connected epsilon component. And maybe the duration, they should be together for some minimum amount of time. Okay, so for example, m equals to 4. The distance between them should be at most epsilon, and then they should walk together or move together for some minimum duration of time. And notice that only maximal groups are relevant, right? And that means that they have to be maximal either in the group size, it could be maximum in the start time, or in the end time. And I'll show examples of this later on. That is actually a bit tricky to keep track of all the groups. And also note that an entity can be in several maximal groups at the same point in time. So look at this, for example. I started red and blue as one group with the green one out. And then they move, and they form one connected component of size 3. They're still a connected component of size 3. And then the green and red continue together while the blue goes off. Right? So at T0 we have 2 groups. Then at T1 and T2 we have 1 big group. And at T3 we have 2 groups. So look at the interval 0 to 2. So there, red-blue forms a connected component. So they form a group. The time 1, 2, we have that red, blue, and green form a connected component. And then if you look at the 1 to 3, well, then we have the red and green as a connected component. So that means at time T2, red will be in 3 groups. Right? And that's because we're looking at the maximal groups both for size, start time, and end time. Good. Okay, so let's say we have 4 entities. We'll look at their epsilon balls and look at this behavior. And now let's say that we would like to show this group structure, how the groups change. Right, so look again, maybe just focus on something here. Let's focus on the green entity, for example. So the green and blue, they will initially form a connected component. Okay, then they will merge with the red one, then the green one will leave and form something with the purple one. Right? So first it's the blue and green, then it will form a bigger group with red, blue, green, then the green will go away and form a group with the purple one. And you want to track these changes. So the two questions I want to look at is, what are the number of maximal groups? And how can we effectively compute all these maximal groups? Okay, so consider the motion of all the epsilon disks over time. Right, so we have the xy coordinates, and then the third vertical coordinate is the z-axis, the time. So how will so what happens with these epsilon disks when I move in time? Well, so it will just be these disks that move horizontally in time, right? So they will form some kind of tubes, and then if I take a horizontal plane and cut them, the intersection will be just a set of disks, right? So it will look something like this. Right, so here we have the disks in the plane, and then the entities start to move, which means that we get these skewed tubes. But if we take horizontal cuts, then the intersection of a horizontal plane will just be a disk again. Okay. So if the complexity of each trajectory is at most tau, then we get a tube for each trajectory, and it has at most tau skewed cylinders that are connected to each other. Okay. And of course the radius of each of these will be epsilon, the horizontal radius. Right? Okay, good. So again, we are interested in the horizontal cross section and in the evolution of the connected components if we look at the horizontal cross sections. So which new connected components form and which connected components will split. So this is captured what is called a Reeb graph. So it's used in topology, right? I don't know how many of you that know it, but it's not really needed. It's a very simple way to model this. So we want a Reeb graph with maximal groups associated to its edges. This Reeb graph to capture the changes in this manifold. Right? So the edges indicate that we have the connecting components, and the vertices, they define some changes in the connected components. So for example, here you have maybe a set of connected components, here you have a set of connected components, and then they merge into a bigger connected component. Okay. Good. So it's fairly easy to see that if we assume that groups only merge, so we always have two groups that merge into one, or one group that split into two, then there can only be four simple types of vertices. So one is the start vertex at time t0. So that has in degree 0 and out degree 1. And it's just the connected component that is you start with. Right? And then the end vertex has in degree 1 and out degree 0. And the merge vertex has in degree 2 and out degree 1. And the split vertex has in degree 1 and out degree 2. Okay. So note that a merge vertex is just when two of these tubes intersect. Right? Because then your connected components will all of a sudden get a connection, and that will form a bigger connected component. Good. So let's look at the worst case. So unfortunately, one can prove that the Reeb graph of this manifold has tau n square vertices and edges. And it's pretty easy to see. So say that we only look at one single time step. Right? And we set half of the entities to move vertically down and half of them to move horizontally from left to right. Then you can place them in such a way that for every horizontal entity, that will form a connected component with every one going vertically. Right? So that means that you will get a quadratic number of components, and this can be repeated over and over again for order of t, omega of tau time steps. So the low bound is tau times n squared. Right? So we cannot do better than that. So there are very few questions today. Are you sure you don't have any questions? Okay. So I just showed that the Reeb graph has complexity at least tau n squared. So now I'm going to try to show that the Reeb graph has an upper bound of tau n squared. So consider two entities during one time interval. Well, of course, two entities can only merge and split once, right, during one time interval. So this interval can generate at most two vertices in the Reeb graph. One merge vertex and one split vertex. So that means that you can get at most a quadratic number for each time step. And since again we have tau time steps, that means that the Reeb graph has at most tau n square vertices. Okay. So let's see if we can compute the Reeb graph. So we take, for every pair of skewed cylinders, we compute the time of intersection. Right? So we have a quadratic number of different entities, and for each entity we will have tau cylinders. But since we only look at time, it means that we don't have to compare every pair of cylinders, but only cylinders at the same time. So that means that computing the time of intersection will be tau n squared. Good. And of course, then we have to sort these events with respect to time, and that will take us tau n squared log tau n. And then we initialize the graph, so that's just looking at all the connected components at time t0. So that will take us at most quadratic time. And then we will handle all the events by increasing time. And okay. And this is, of course, very easy, right? You have the connected components, and then you have all the events. So you know exactly when a change will happen. Okay, so you will know exactly when these two will merge, and you put a vertex there, and you add the two edges, and you continue like this. But this only gives you the graph, right? It doesn't give you any more information than that. But this can fairly easily be done in tau n squared log n time. But now we have the Reeb graph, but we don't actually have much information in this Reeb graph. Right? Okay, so it can be computed in tau n squared log n. So each entity, if you look at this again, you can see that each entity will follow a path in this Reeb graph. Right? So say that you have an entity that starts here in this connected component, then it will form a path in the Reeb graph from a start vertex to an end vertex. Okay. So we start at an start vertex and an end vertex. And now my claim is that there are at most tau n cubed maximal groups. And the proof is fairly the idea of the proof is simple. You have tau n squared vertices in your Reeb graph, and I'm going to prove that there is at most a linear number of maximal groups that can start at a start or merge vertex. Right? So that will immediately give you the bound. Is that clear? Yeah. Okay. So, for example, okay, so let's consider a merge vertex. So, say we have a set S here and a set T here, and they merge. So they become a connecting component. And then let Px denote the path of entities, the path of an entity X. Right? So this entity X belongs either to S or T, and we just want to track its movement in the Reeb graph. Okay? Is this clear that you're following the path of one entity in the graph? If not, just someone can just shake their head. That doesn't count. Okay, let's see. So you have two connected components, right? And they merge at this point here. Now these two connected components will have a lot of entities. So now I will track all of the paths of all those entities. But if I pick one entity, say X, then there will be a path in the Reeb graph all to the end of the Reeb graph, right? All the way till I hit an endpoint. Okay, so now I want to track all these paths. So consider the union of all such paths, right? So this is the paths that are formed by all the entities in S and T. Okay, so let's call that union R prime. So it's fairly easy to see that this is a directed graph from bottom to top. It's an acyclic subgraph of the Reeb graph. Yeah.
The Reeb graph, for every entity we have a trajectory, isn't it?
Well, for every entity there will be a path in the Reeb graph.
So now you have S and T set of entities.
Yes.
So these are not the passes in Reeb graph. These are not the entities of the Reeb graph. In the Reeb graph we have the path for an entity for each entity, and here we have the group of entities.
Yes, but you have a group of now here you have so in the Reeb graph you actually have a group of entities, right?
So how do you track a specific entity when the Reeb graph is for several entities?
So, for example, you have, so say you have something like this. Here we have 1, 2, and maybe 3, 4. Maybe they'll merge. So then you get 3, 4, 1, 2, 1, 2, 3, 4. And then maybe they split here to 1, 3, and 2, 4, and so on. Right? So now I track, say, number 2. Right? So number 2 will just be this. Right? This is the path that describes the movement of
For example, S here is the setup of one entity.
Yep. Yep. Very good. Very good. Okay, so now I'm going to try to unravel this graph. So I'm going to try to remove all the cycles. Okay, and the idea is very simple. If P and X, if I have two paths that first split and then merge, I'm actually going to consider them as two separate paths. Okay. So I'm going to duplicate the path starting at the split vertex. Right? So say that I have, this is my original graph, my original directed acyclic graph. And now I want to try to unravel it. So let's look at the two paths px, py. So the only thing I want to do now is when they merge, I just duplicate them. Okay, so I get this instead. And now I take the next cycle from top to bottom. I split that. Then I take the next one. I split that. And at the end, I know that every vertex will end up at an end vertex. Right? So note that the number of end vertices is bounded by order of n. Right? It's bounded by n. Is this clear why this is? Right? Because here you have two paths that merge, which means that you will have two paths that end in this end vertex. So it's okay to split them up, right? Then I will get one in each end vertex. Good. Okay, so if I look at a maximal group, it can only end at an end vertex or end at a split vertex. So now I'm looking at the group again, right? So of course, a group can end at an end vertex. There's nothing else you can do from the end vertex, so it could finish there. But of course, it can only also end at a split vertex. Yes. Okay. So the number of leaves is at most the total number of entities in S and T. And we know that has to be bounded by n. And we know that all the split vertices have degree 2. Right? So that means that every vertex has, so it has out degree at most 2. So the total degree at most 3, which means that, again, we have only a linear number of split vertices. So now a group can only end at an end vertex or a split vertex. So since there can be at most one maximal group starting at V and ending at the split vertex, and at most one maximal group starting at V and ending at an end vertex, the number of maximal groups starting at V is bounded by order of n.
Sorry, why the number of your leaves is not exactly n?
Because it could be that there are two entities that actually go together until the end. So they don't split. Well, the merger could be below V. Yeah. Okay, so that means that we have that the bound is tau times n cubed, right? We have tau n squared vertices in the reed graph, and each vertex, at most a linear number of groups can start. So that gives us that the bound is tau times n cubed. So there's a lot of groups, right? Unfortunately. Unfortunately, it's tight, yes. So I guess what would be interesting if one could add some constraints to it to get so, because this says that everything can happen, right? So maybe it would be interesting to see if there are some natural constraints that would get down the number of maximal groups. Okay. So let's say that we are given a set of trajectories and we get the three parameters, m, delta, and epsilon. Right? So m is the number of entities in a group, minimum number of entities in a group. Delta the minimum duration, but let's ignore delta for now. And epsilon is just the spatial error, or the spatial distance that they have to be close to each other. So then we compute the reed graph using the distance epsilon, and we know that can be done in tau n squared log tau n, And then we need to process the vertices in time order to maintain the maximal groups. So because what we want to do with this graph, we want to put the information of all the maximal graphs in on the edges. Right? So for example here we have actually the same example. As here we have 4 vertices starting. So that means that for each of these edges we have a maximal group with 1 starting at time t0. 2 starting at time t0 and so on. And when they merge we get 3 is a maximal group because it started at time t0. Right? So it's longer than the group containing 3, 4 because that one started at time t1. Right? So this one is maximal with respect to the duration, while this one is maximal with respect to the number of entities. Okay, so that means that I would like to store 3 starting at t0, 4 starting at t0, and connected component 3, 4 starting at time 1. And I do the same here. And then for this one, I will get all of them. Right? So I get 1, 2, 3, 4. All of them will start at times t0. So again, they're maximal in time. I will get 1, 2 starting at t1, 3, 4 starting at t1, and then 1, 2, 3, 4 starting at t2. And then they will merge, then they will split, and again I have to recompute all the sets. So the question is, how can I compute all these sets? Right? So I have my graph, but now I want to put all this additional information on the edges. And again, it's quite a lot of information, right? So we know there could be tau n cube number of groups in total. Okay. Okay, so again, each edge E is labeled with the set of maximal groups. So let's call that G of E. And note that a group G becomes maximal at a vertex. Right? So, for example, let's say look at the start vertex. Then the connected component, the entities in the connected component corresponding to the start vertex, that will be your first group. Good. And the time that starts is at time t0. Or whenever it starts. I mean, I guess it could actually start later on, but assume it starts at t0. Then at some point you go up and you get a merge event. So that means we want to propagate all the maximal groups from the children up to the new edge. So note that all the groups that were maximal groups before will still be maximal groups after the merge. Right? So we take all the maximal groups that we have before in GE1 and GE2, and then we add a new maximal group. And the new maximal group you get is the union of these entities and these entities. Right? And of course, the starting time of this is at vertex V. So time TV. Good. Is that fair? Yep. These ones? Well, so note that these are only max. They started earlier, right? They start at time t0, while these only start at t1.
Does it matter if we have from t0 to t4 we have 1 and 2, but in between 1 and 2 we're part of a bigger
You're right that they're part of a bigger group, but the bigger group is only valid for a very short time. So if I want to say I want to find, a maximal group between T1 and T3. That starts at T1 and ends at T3, then I cannot take this one. I want all the maximal groups, so that includes also starting time and end time. So more or less the reason for this is that you can have a very big group for a very short time, but maybe that big group is not very interesting. Right? Okay. So here we have the merge vertex. So we just take all the groups from the children, and then we add the union of the entities as a new group. And this one will start at the time TV. Okay. Now the split vertex is a little bit trickier. So we have a vertex V, and that splits into two edges, G1 and G2. So what can happen at the split vertex? Anyone? Any ideas?
What can happen? The number of groups will be much less.
Yeah, so you're saying that a group will disappear. Can you create a new group? But
Yes. For example,
you have to decide.
that's two slides before this. We have 1, 2, and for example, we have 1, 2, and 3, 4, and they merge together with 1, 3, and 2.
Yes, exactly right. Here you split, and you get a new group. Right? This group has not been there before, so you actually create a new group. So you also delete, you end a few groups. So you can have that the group just continues like this, 1T0. That a new group is created, like 1, 3. And that an old group ends. So you can have all these three events. So a group may end at V, a group may start at V, and a group may continue on E1 or E2. So how can we compute these groups efficiently? So that's the main question we're going to look at in the remaining slides. So just first a simple observation that says that, so let's say I have two groups, S and T, that is stored on my edge E. Right? So let's assume, for example, that S starts at TS and T starts at TT. Right? So just note now that, I've drawn it like this, but actually T could be on the path from TS to this one, right? Right? And then, of course, there must exist a group that contains all the entities in S and all the entities in T. Right? Because at some point they merge, and that will create a new group. And of course, since we have all the entities in T and all the entities in S, the union of these must be part of some group. Okay, so that group has to start after TS and TT. A nice observation here is also that, say that S and T have a non-empty intersection. Well, if they have a non-empty intersection, that means that S has to be a subset of T, or T has to be a subset of S. Right? Why is that? Sorry? Yeah, I think you're on the right. So if there are entities here and entities here that belong together, that are the same, well, that means that TT actually, all the entities in T actually has to be a subset of S, right? It cannot, you cannot merge and only have a subset of your entities, right? So that means that, for example, if T is a subset of S, then TT has to lie here on this path. Good. So S and T are either disjoint, or S is a subset of T, or T is a subset of S. Okay, so now I'm going to look at all the groups for E. And to speed up my computation, I'm going to store that all these in a tree, so I can do some efficient computation on it. Okay. So let's look at this set of groups, and I just put it in a binary tree. Right. So I have my largest group, 1, 2, 3, 4 is the root, and then because of the observation, it will either be a subset or disjoint, right? So it's either disjoint or a subset, so you can easily buy this hierarchical tree. Okay. So just remember, I have more or less the same structure, but all the groups are stored in a tree, not in some kind of linear order. Okay, so this is just to recap. So a split vertex, a group may end at V, a group may start at V, or a group may continue on E1 and E2. And of course the first ones are fairly easy to do quickly, right? Because it just says as a start vertex, well, you only have the group you started with, and at a merge vertex you just take the union of the two and then just add one new group. So that can all be done very quickly. So the only problem we have is at the split vertex. How do you actually compute a split vertex? Okay, so here again, this is what we have, and we split and we get some new groups. And we have the following tree structure for this edge. And now we want to compute the two tree structures for these two edges. And we want to do it as fast as possible. Okay? So the only thing we do is we just traverse all the vertices in this tree bottom up. Okay, so we start at the bottom. Well, we have 1 and T0. Well, we just put it in our tree corresponding to this edge with 1 and T0. Right? This is still a valid maximal group, and we want to keep it. Then we go up and we get, of course, 2 and 3 and 4. And so 2 and 4 is on this edge, 1 and 3 is on the green edge. Then we continue. And the only thing we do is more or less track these vertices. So this one belongs to the green edge. We track it up to its parents and see that there is actually 1 green and 1 purple. So they do not form a group, right? Because they do not actually walk together anymore. So you don't do anything until you get to the top. And at the top, you just start to merge bottom up. Right? So you have 1 and 3. Well, that means that you will have 1 and 3 starting at, starting at T3. And that's it. Right, so it's fairly simple bottom-up processing. So a start vertex can be handled in constant time. The merge vertex can be handled in constant time. The split vertex will take linear with respect to the size of this tree. So that is linear with respect to the number of groups you have on that edge. Okay, so that's bounded by n. So since the total number of vertices in the Reeve graph is tau n squared, and now we get a linear bound for each edge, that means that we get a bound that is tau n cubed. And then, of course, it depends on what you really want to output. There are various different ways to decide what you want to output, but in general it takes tau n cubed. So here is it's a nice picture made by, I think, Kevin Bochen, where they look at the groups. Right? So he tries to visualize the groups. So here you say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 15 trajectories. And here we want to find all groups of size 3 walking together. Okay, so these colors, so for example, if you look at a yellow region, that means that you have a group of size 4. And for convenience, he has put the x-coordinates as time. Right, so here you can see how the group structure changes during time. So you have some very long groups with a few number of entities, and you have some fairly short groups with a lot of entities. Right? And of course you can start to play around with these parameters. So if you require a smaller group size, well then you will get more groups that are longer. And if you want larger group size, well then you will get fewer groups. And of course you can also change the duration so that you have a minimum duration on it. So for example, you can decide to only report very long duration groups, or you can decide to also report short duration groups. And and in their paper they also look at robustness. So when we did the computation, we said, if the connected component, if two connected components start to overlap, then we will immediately create a new connected component. So you can again play around a little bit with that. So you can say, well, say that you have these 6 entities, and for some reason one of the entities leaves the group for a very short time. Well, maybe you will still want these to be considered one group. So what you can do is say, well, I require that there is some overlap in some time span. So maybe I don't really need them to be together all the time, but I need them to be together most of the time. Right? So this is fairly easy to handle in the Reeve graph. So if you just have very short edges with respect to time, you can just merge them. And again, you get exactly the same bounds. And they also did some experiments that I just stole their slides. And it just indicates the duration and size of the groups. Okay, so to summarize, they presented a model for the grouping structure of moving entities, which I think was really missing from the community. I think that's a good thing that they did. And they show arguments for computing these grouping structures. And in the beginning, I showed you a lot of different movement patterns. Most of these are some kind of group patterns. So my guess is that there are quite a lot of open problems here. So I think one of the trickiest things is what is an interesting movement pattern. And maybe us as computer scientists, we find it a bit hard to see what is an interesting pattern. So I think if you would like to do something on movement patterns, maybe just talk to people that track things and ask them what kind of patterns are they looking for. And maybe you can just think about what would you be interested in if you say, take something you like, say football, and assume that you're tracking football players. What kind of patterns would you be interested in? Does it make? And then, of course, afterwards you have to say, does it make sense? And does the definition make sense? And is it even possible to compute it? So one problem area that I haven't discussed much is query version. So everything I do, more or less, is taking all the data and then you compute something, and that's what you output. But there's very little work on query versions. So, say that I'm giving a region, and now I would like to report all groups in that region or something like that. I mean, there's nothing like that as far as I know. And of course, if you speak to experts in other fields, what they really want to do is automatically set the parameters. So as I showed you here, I assume that you're given, say, the group size, or I'm given the delay in the single file, or whatever it could be. But, users don't want to set these parameters, right? They really would like to get everything computed to them. So, is there any way you can compute these parameters yourself? And that's it. Thank you very much. Any questions?